Section: Introduction. In this section, we explore the ideas presented by James P. Carse in his work, Finite and Infinite Games, A Vision of Life as Play and Possibility. Carse distinguishes between two types of games: finite games, which are played to win and have set rules and endpoints, and infinite games, which are played to keep the game going, with flexible rules and no fixed boundaries. Traditional video games are typically finite due to the constraints of programming and graphics, where all actions and rules must be predefined. However, we believe that recent advancements in generative models have opened the door to creating the first generative infinite video game. Two key developments have made this possible: large language models, LLMs, that can manage ongoing game mechanics and generate interactive narratives, and visual generative models that create high-quality images based on prompts. We introduce Unbounded, which we consider the first interactive generative infinite game. In Unbounded, AI models generate game behaviors and outputs, moving beyond the limitations of traditional coding. The game takes inspiration from sandbox simulations and digital pet games, as well as tabletop role-playing games that allow for limitless storytelling. Unbounded features a gameplay loop focused on character simulation and open-ended interaction. Players can create their characters, defining their looks and personalities, and the game generates a world for exploration, interaction, and conversation. The game continuously creates new scenarios and challenges based on player choices, offering a unique and infinite experience. Specifically, Unbounded includes 1. Character personalization. Players can create their characters. 2. Game environment generation. A persistent world is generated for exploration. 3. Open-ended interaction. Players can use natural language to interact without predefined rules. 4. Real-time generation. We achieve significant speed improvements, with new scenes loading in about 1 second. Our technical innovations include a specialized LLM-based game engine that maintains consistent mechanics and generates coherent narratives in real time. This model is fine-tuned using data generated by 2 strong LLM agents, eliminating the need for human input. In visual generation, we present a new regional IP adapter that ensures consistent character and environment generation. This adapter conditions image creation based on the game environment and character appearance, reducing interference between the two. Our contributions are both conceptual and technical, introducing the idea of a generative infinite game and showcasing its potential for interactive entertainment. We provide a new framework for game design where logic and content are driven by generative models. Our main technical advancements include the specialized LLM for game logic and the regional IP adapter for visual consistency. We demonstrate the effectiveness of our approach through evaluations that show improved character and environment consistency, as well as interactive speed comparable to larger models. In the related work section, we discuss controllable text-to-image generation, which is crucial in diffusion model applications. Techniques like ControlNet use various control signals to guide image generation, while other methods focus on layout control for object placement. Personalization is another key area, aiming to create consistent characters across generations. However, many existing methods struggle to condition characters and environments separately, often requiring predefined masks. Our improved regional IP adapter addresses this issue by enhancing consistency in character and environment generation. Section Summary. In this section, we introduce Unbounded, the first interactive generative infinite game that leverages advancements in large language models and visual generative models to create a dynamic, open-ended gaming experience. Our approach allows players to personalize characters and interact with a continuously evolving world, while our technical innovations, including a specialized distilled LLM and a regional IP adapter, ensure real-time generation and visual coherence between characters and environments. Section: Large language models in image generation. In this section, we explore the use of large language models in image generation, highlighting their strong ability to learn from context. These models can tackle various tasks, such as generating image layouts from prompts and facilitating interactive image creation. Our focus, however, is on developing a specialized language model that acts as a game engine, generating game mechanics, stories, and character interactions. We introduce Unbounded, an interactive and endlessly generative game that utilizes text-to-image models and large language models. Unbounded provides several features. 1. Users can create personalized characters with unique looks and traits. 2. It generates a persistent and interactive game world. 3. Players can engage with their characters using natural language, prompting the game to create new scenarios based on their actions. And 4. It operates with near real-time interactivity, refreshing almost every second. We will explain the methods that enable these features. A standout aspect of Unbounded is its real-time interaction capability, achieved through latent consistency models, LCM, that allow for high-resolution image generation with minimal steps. By using LCMs, we ensure quick text-to-image generation, essential for an engaging gaming experience. To support custom characters, we integrate Dreambooth into our model. We fine-tune the diffusion model with a set of character images, adding a unique identifier to represent the character. This fine-tuning merges subject-specific adjustments with the LCM, effectively maintaining both speed and character integrity. While other personalization methods exist, they often struggle to preserve character features, which is crucial for a satisfying gaming experience. Another important feature of Unbounded is the ability to generate characters in specific environments while performing actions based on user input. We must ensure both character and environment consistency. While we have addressed character consistency, we face challenges in maintaining environmental consistency and accurately placing characters without misalignment to text prompts. Existing methods often fall short in achieving this at interactive speeds. Therefore, we propose a new regional IP adapter that consistently places characters in predefined environments according to text prompts. Our regional IP adapter enhances the original IP adapters by allowing dual conditioning for both characters and environments. This means we can generate a character in a specified environment simultaneously. For example, if the prompt describes a witch in a desert, the model must generate the character next to cacti in that setting. Our approach uses a dynamic mask-based method that separates attention for the character and environment, preventing interference between the two. We calculate attention maps between the character's text and the model's hidden states, dynamically updating masks throughout the process. This allows us to generate characters without environmental interference, improving character consistency while ensuring the background aligns with the environment image. Section Summary. In this section, we present Unbounded, an interactive generative game that utilizes large language models and text-to-image generation to create customizable characters and dynamic worlds, enabling real-time gameplay. We introduce a regional IP adapter that enhances character and environment consistency by allowing dual conditioning, ensuring characters are accurately placed within user-defined environments while preserving their features and following text prompts. Section: Blockwise drop on environment conditioning. In this section, we discuss our approach to blockwise drop on environment conditioning. For our regional IP adapter, we utilize a dynamic mask created from the cross-attention between character text and hidden states. The effectiveness of this mask is crucial for distinguishing between character and environment generation. We observe that in the down sample blocks, the attention spreads across the entire image rather than focusing on the character. This suggests that the diffusion model does not effectively separate character and environment generation in these layers, instead concentrating on the overall image structure based on text prompts. This finding aligns with previous research indicating that down sample blocks emphasize spatial layouts, while up sample blocks focus on style. Consequently, we decide to eliminate the regional IP adapter from the down sample blocks and use it only in the mid and up sample blocks, which enhances the spatial layout generation between character and environment. Furthermore, we discover that incorporating dynamic regional IP adapters in the up sample blocks better aligns the generated background with the conditioning environment by extracting relevant semantic information while maintaining character-specific details like appearance and poses. Next, we introduce Unbounded, a language model game engine that simulates character actions in predefined environments using images generated from scene text descriptions. It allows users to interact naturally with the character and the game environment. For instance, users can take the character to various environments or perform open-ended actions like petting the character and then taking them for a rocket ride at a space station. However, this expansive interaction presents several challenges. 1. Environment binding, where the model must correctly place the character based on user instructions. 2. Coherent story generation, ensuring the narrative and character responses align with specified traits. 3. Game mechanics generation, which involves monitoring the character's state and updating it based on interactions. And 4. Prompt rewriting, where the model must adjust narratives for the diffusion model to ensure consistency. We find that a large language model, such as GPT-4, can handle these tasks effectively, but its high latency makes it impractical as a game engine. Therefore, we propose distilling these capabilities into a smaller model, Gemma 2B, which can support real-time interaction. We then outline our character life simulation game, which involves 2 LLM agents. One agent acts as the world simulation model, responsible for creating game environments, generating narratives, tracking character states, and simulating behavior. The second agent serves as the user model, simulating player interactions with the world simulation model. Users can continue the story, move the character to different environments, or interact with the character to maintain their health. Users can also provide personality details or guide character actions, influencing the simulator's narrative generation. This interaction between the 2 LLMs creates a dynamic character life simulation game with endless interaction possibilities and narrative paths. Finally, we present our framework for distilling the capabilities of larger LLMs into a smaller, more efficient model using synthetic data generated by stronger LLMs. Our framework consists of 2 steps: 1. Automated data collection, and 2. Small model distillation. In the first step, we aim to create a general-purpose character life simulator by gathering a diverse dataset of topics and characters. We prompt a large LLM to generate pairs of topics and main characters, ensuring diversity by retaining only those pairs with a Rouge L similarity below 0.7. This results in 5,000 unique topic character pairs for user simulator interaction data. In the second step, we collect multi-round interaction data between the world simulation LLM and the user LLM. The world simulation LLM sets up the game environment and initiates character actions based on randomly sampled topic character pairs. The user LLM then provides interaction inputs, and the world simulation LLM generates updated character actions and states. This iterative process continues for 5 interaction rounds per session, yielding a total of 5,000 user simulator interaction examples. All prompt templates are included in the appendix. Section Summary. In this section, we describe our approach to enhancing character and environment generation in a simulation game by using dynamic regional IP adapters selectively in upsample blocks, which improves spatial layout and semantic alignment. We also outline our framework for distilling capabilities from large language models into a smaller, efficient model for real-time character life simulation, supported by a diverse dataset of character topic pairs and multi-round interaction data. Section: Distillation. In this section, we describe our process for distillation. After gathering interaction data, we fine-tune the smaller Gemma 2B model using 5,000 synthetic user simulator interaction samples. During this supervised fine-tuning, we ignore the loss from user input data, concentrating on optimizing the world simulation model's behavior based on the history of interactions and the current user input. This method allows Gemma 2B to mimic the capabilities of larger language models as a game engine while enabling real-time interaction. Our distilled Gemma 2B shows performance similar to GPT-4o, effectively responding to user input and facilitating unlimited interactions. Next, we evaluate our image generation method. We create an evaluation dataset with 5,000 triplets of character images, environment descriptions, and text prompts using GPT-4o. This dataset includes 5 characters, dog, cat, panda, witch, and wizard, 100 varied environments, and 1,000 text prompts. We assess the image generation based on 3 criteria: consistency of the environment, consistency of the character, and alignment with the text prompt. To measure how similar the images are, we use tools like ClipEye, Dino, and DreamSim. We label the similarity between the reference environment image and the generated images as ClipEye for environment, Dino for environment, and DreamSim for environment. Similarly, we label the character reference image comparisons as ClipEye for character, Dino for character, and DreamSim for character. We also use ClipT to check how well the images align with the text prompt. Since Unbounded is a character life simulation game, it's crucial to confirm the character's presence in the images. Therefore, we apply grounding Dino to detect the character in the generated images, setting similarity scores to 0 and distance scores to 1 if the character is absent. For evaluating our language model generations, we gather another dataset with 100 user simulator interaction samples. Each sample consists of 5 rounds of interaction between the user and the world model. We use GPT-4 to score the responses from our model against a baseline model, assessing overall performance and 4 specific aspects: accuracy of character state updates, relevance of the environment, coherence of the story, and adherence to user input instructions. Scores range from 0 to 10. Regarding implementation details, our image generator is based on SDXL. We train a Dream Booth LoRa with a rank of 16, using a batch size of 1 and a constant learning rate of 0.0001 for 500 steps on a single A100 GPU, which takes about 30 minutes. We prepend the special token, SKS, before the character during inference. We combine the LCM LoRa with Dream Booth LoRa at a scale of 1 for each. For encoding the environment, we use IP adapter plus SDXL VIT-H, and for the character, we use IP adapter plus face SDXL VIT-H. The dynamic mask ratio is set to 60%. Our language model is built on Gemma 2B, distilled using 5,000 user simulator interaction samples from GPT-4o. We train the model for 6,500 steps with a batch size of 8 across 4 A100s, using a learning rate of 0.0001. The learning rate scheduler follows a cosine annealing pattern, with a warm-up steps ratio of 0.03. During evaluation, we generate responses using sampling with default hyperparameters. Finally, we compare our regional IP adapter with block drop against previous methods for maintaining environment and character consistency. We merge the character LoRa and LCM LoRa with the model for efficient inference and improved character consistency, allowing for a fair comparison. Our results show that our approach consistently outperforms earlier methods in maintaining both environment and character consistency while achieving similar performance in semantic alignment. Specifically, we surpass story diffusion by notable margins in character and environment consistency metrics, demonstrating the effectiveness of our method. Qualitatively, our regional IP adapter with block drop consistently produces images with high character consistency, while other methods may struggle to include the character or create inconsistent appearances. Additionally, we illustrate that our approach effectively balances environment and character consistency, unlike other methods that may generate environments that do not match the specified conditions. Section Summary. In this section, we fine-tune the smaller Gemma 2B model using synthetic user simulator interaction samples to replicate the capabilities of larger LLMs, achieving performance comparable to GPT-4o. We also evaluate our image generation and LLM responses through various criteria, demonstrating that our approach consistently outperforms previous methods in maintaining environment and character consistency while ensuring strong semantic alignment. Section: Effectiveness of Dynamic Regional IP Adapter with Block Drop. In this section, we demonstrate the effectiveness of our regional IP adapter with block drop for accurately placing characters in environments based on text prompts, while ensuring consistency between the character and the environment through ablation studies. Our results show that adding block drop significantly enhances both environment and character consistency, with improvements in our evaluation metrics compared to the multi-IP adapter approach. We observe an increase of 0.291 in one metric and 0.264 in another, along with better alignment between the text prompt and the generated images. Additionally, our regional IP adapter maintains character consistency and text alignment while achieving similar performance in environment consistency. We also examine the impact of the environment IP adapter scale, finding that a smaller scale generally boosts character consistency, although it slightly reduces environment consistency. Qualitatively, we find that conditioning on the environment using the IP adapter leads to good environment reconstruction, but character consistency is still affected by the environment style. The introduction of block drop enhances adherence to the text prompt, resulting in images that correctly position both the character and the environment. However, the character's appearance is still influenced by the surrounding environment. By integrating our regional injection mechanism with a dynamic mask scheme, we achieve strong character consistency while effectively conditioning on the environment. Next, we show that our diverse user simulator interaction data successfully distills the Gemma 2B model into a capable game engine. Our findings indicate that zero-shot inference with smaller language models results in lower performance compared to our approach, emphasizing the need for distillation from a stronger model for simulating game worlds and character actions. We also demonstrate that our model performs comparably to GPT-4o, confirming the effectiveness of our method. Furthermore, we investigate how the size of the distillation data affects performance, comparing models distilled with 1,000 and 5,000 data points. Our results consistently show that using a larger dataset improves performance across all metrics, suggesting that further enhancements could be achieved with even more data to match GPT-4o's performance fully.